CN that it thinks it sees and generating that a certificate with that common name. Or it can say, well, I've got this big batch of crap. The only thing I care about and it looks good. Let's go ahead and allow that. That's the easy way to do it. That's actually the OpenSSL way of doing it. That is vulnerable to a bunch of attacks. So let's actually look at what OpenSSL does when it does the certificate authority signing. There are three ways that OpenSSL makes it easy to implement a certificate authority. The first way is you just go ahead and do the signing, and then you take this string here of the subject, and you see if you approve of it. Oh, there's cn.www.foo.com, is that okay? The second way is to dump the request and see if you approve of the contents of the dump. So you take this request that comes in, you dump it, you check the subject there. Or you can go ahead and dump the generated certificate and audit the subject. So you generate it, but instead of taking the output of the generation command, you dump the certificate and see if it's good before you send it to the user. Now, this should obviously bring to mind the idea of injection attacks. What if you have a string in there that says, oh, organization, my organization is badguyincorporated/cn equals www.badguy.com. And indeed, you get a straight-up injection in the output of all three of the tools. You'll get O equals badguy.com/cn equals www.badguy.com. Now, OpenSSL can defend itself from this. There's an option called nameopt. There's 4 different values you can put in there. All 4 of them are secure against this sort of injection. Not a single one of them is enabled by default. Damn. Now, is this exploitable? Well, it depends on the particular certificate authority, how they actually handle multiple common names. It turns out, however, interestingly enough, a genuine x509 subject name could contain multiple common names. You have an organization, a city, a state, a common name. What if you have another common name? What if you have 3? What if you have 4? What if you have 5? That's not actually defined, it turns out. And it turns out it totally depends. If you have OpenSSL, the first common name wins. If you have Crypto API as part of Internet Explorer, all common names. It's an all-inclusive policy. And if you have NSS with Firefox, the last common name is the one that the browser actually validates. Now remember, the certificate authority is trying to communicate with the browser. The certificate authority doesn't know which browser it's talking to, and all the browsers will hear different things. So first, all-inclusive last, we actually have a fail policy. How great is that? So, now it's usually that OpenSSL screws this up and only provides you the first certificate. It is possible to use the API securely. However, if you actually look in the field, you will find clause and Open1X and wget and bacula. Everyone just uses this x509 name get text by nid call. And it always only returns the first common name. If you have a certificate authority that is using this API, it too is only going to see the first common name. So what do you do with this? Well, the first thing you do is you need to be aware of wildcard policy. If NSS inside of Firefox sees a common name of star, it just assumes, well, okay, it's a God-level cert. This can sign for everything. Internet Explorer is a little more paranoid. It basically says, if I see star and assert as the top level and that's it, this CA probably got hacked. And it just like chickens out and refuses to do it. So what you do then is you create a PKCS10 request with 3 CNs. The first being the attacker.com CN, because that actually is going to be validated against the attacker. The second is going to be www.bank.com, because you can still specify individual hosts for Internet Explorer, because Internet Explorer is going to see all 3. And then you round it out with just a star. So against Firefox, you get to spoof all names whenever you want. Now, we get to have some more fun. Now we get into some wonky stuff. What is a common name? Like, what is it actually, how is it represented on the wire? ASN1, who here is familiar with ASN1? I am so sorry. This crap's got like 3 ways of representing a length and 13 string types. What is wrong with these people? So ASN1 was designed to be very fast to parse. It's actually very fast to crash under fuzzing. It's really, really hard to write a solid ASN1 parser. When the Protos guys actually fuzzed ASN1 in 2002, they pretty much broke every router on the planet. Now, it turns out that this ASN1 is a channel for SQL injection. And this is great. It turns out XKCD and little Bobby tables helped secure the internet. I swear to God, it went exactly like this. Little Bobby tables came out, it got passed around a bunch of geeks, and the certificate authority guys were like, holy crap, someone could put a drop statement in there. Actually happened, according to Peter Gutman. In ASN1, common name is not addressed with the characters COMMON space NAME. I mean, that has like language translation issues. So what they do is they put everything into kind of a numeric namespace. So instead of 2543, instead of common name, you say 2.5.4.3. And that would be what's called an OID, an object identifier. 2543 is the only object identifier that is actually cared about between the certificate authority and the browser. Everything else is ignored. But how is 2543 actually put on the wire? I'll tell you, it's not 2 period, 5 period, 4 period, 3 period either. No, that would be too easy. What actually happens is ASN1 basic encoding rules, BER, is a tag length value format, meaning you have a tag, some value that describes a type, 6 being the type of OID, and then a length, which can be encoded one of 3 ways, and you really don't want to know them, and then a value, which is a certain number of bytes of whatever the length was. Now, in the values of OIDs, you have, it's what's called base 128, which means a number can be encoded one of 2 ways. You could either have, say, a 6, which is just, this is a .6, or it could be 86, which says, this is the number 6, and there's another number coming. It's like place value. You know, you have the 1s, the 10s, the 100s. Only it's the same for like the 128s, the 128 times the 128s, the 128 times, you know, so on. Base 128 representation. So in the really simple mode, this is what a simple OID looks like. You have a 4 and a 3 for .4.3. For a slightly more complicated representation, we have, look at that right there, 86 times 4. We have an OID of 1.2.840.113.549.1.1.1. No, I don't know why they made it so complicated either. But what I want you to look at is the 8648. What that says is, take 6 times 128, so 86 minus 80 is 6, so 6 times 128 plus 72. 72 is the decimal representation of the 48. That's 6 times 128 plus 72 is 840, and there's the 840 at the top of the OID. Kind of making sense. You have like the capability for various numbers to chain in a row. So this is interesting. First off, you can have leading zeros. So instead of 2543, you can do the hexadecimal equivalent of 25403. Because 80, that's 0 times 128, which is 0, plus 3. So you actually can have an arbitrary number of 80s before the 3 in 2543. What happens? Well, OpenSSL is not fooled at all. It's actually